All right. Whoa. Okay.
Testing, testing, 1, 2.
Okay. Well, that's being fun. Welcome to United Astronomy Clubs of New Jersey. Thank you for joining us here in the state park. So, well, I'm just going to give any last-minute stragglers a chance to wander down. Welcome. Those online also welcome that because we are in fact live streaming these to both YouTube and Twitch. So if you ever can't make it up here in Hope, New Jersey, you can always join us online and say hi in chat. I love when people ask questions there. Let's see if that's is that a little bit better? Yeah, that sounds a little bit better. Less like I'm too loud. So, you can check us out on our website, uacnj.org. It's where you're going to find a list of all our upcoming talks. It's probably where you found this upcoming talk, and you can see all the future talks. But if you see one that's already passed and you're like, man, I missed it, do not worry. We do save those on our YouTube channel. You can also check us out on our social media feeds, our Facebook, Instagram. We have a Discord server, all great places to find out what we're up to, as well as get information on events we're doing. That speaker is really going to drive me nuts. Um,
That's called percussive maintenance.
occasionally it works. Um, sorry. So, for those of you here, couple safety briefing things. If you do need to use the restroom, it is the porta potty in the back to my left, your right. When we go to leave here, we are using our headlights because, as much as we love our night vision, we prefer not getting run over. Uh, Big thing there, way too much paperwork if we get run over. So let's avoid that. If we are wandering around with any sort of flashlight, do try and keep those pointed towards the ground. We don't need to accidentally blind people because we're doing fun flashlight laser raves, so avoiding that. We do have a couple of scopes open. It's a bit overcast, so we're going to be trying to see objects in the random holes that pop up through the cloud cover, if any pop up through the cloud cover. Because when it gets dark, it's hard to see clouds, oddly enough. Uh, and there will be volunteers at each of these scopes. Do listen to them, ask questions. We'd love to hear them. We also have a little museum area and gift shop that I will be manning after the presentation because they do not allow me to be in two places at once because that's way too much power for any one person to have. He's laughing because he knows how much damage I would do if I could be in multiple places at once. But you are not here to hear me ramble on, as much as I've been doing a great job of that tonight.
You're here to hear me ramble on.
This is Dan Kirby. He's going to be giving tonight's talk everything you wanted to know about astronomy, but we're too afraid to ask. So we are going to have the presentation and then a question and answer session at the end. So, Dan Kirby has a bachelor's degree in physics and a minor in history and a master's degree in computer science. He has been an amateur astronomer since childhood. He's a member of the board of Amateur Astronomers Association of New York and on the board of United Astronomy Clubs in New Jersey, us here. He is also the site coordinator for AAA's activities here at Jenny Jump Observatory. He has spent many a lonely night here, and I always rag on you because more often than not you have your huddle, your group of astrophotographer friends up here with you. You're not spending lonely nights here.
Me and the boys.
Here at Jenny Jump, wandering between the stars. And while astronomy is by far Daniel's most passionate hobby, he also enjoys reading, cycling, camping, riding self-balancing personal electric vehicles, and for his day job, Dan's a software engineer. And he has Instagram and whatnot. He'll probably shamelessly plug later.
There's a very shameless plug in the end of this at the end of the slide deck. Yeah. So just you got my introduction, but just a little bit about me. This is a news article that was written about me.
Did someone take my chair? Yeah, I kind of need that.
For those watching online, somebody borrowed Kim's chair. So this is a news article that was written about me in 2006. So you can do the math on how old I must be now. As mentioned, I'm a software engineer. I'm on the board of 2 local astronomy clubs here in the New York area. I do frequent talks on astronomy topics, and I have a lot of experience talking to people about astronomy literally on the street, because one of the big parts of astronomy is what we call sidewalk astronomy, where we'll take telescopes to a public place and show people, the moon and the planets, get people excited about astronomy. So I think I have a decent idea of like what the average person knows about astronomy, and my goal for this talk is sort of to like have a target audience of basically anyone, and the motivation is that most people generally don't understand much about astronomy. Our ancestors had a much richer connection to the sky because they didn't have Netflix. When it was nighttime, they just went out and looked at the stars. They knew the patterns of the sky. They knew, which stars meant it was time to plant, which stars meant it was time to reap. But our society, because of our modern science, knows more about what's actually going on up there. So my goal for this talk is to kind of like bridge those two and to allow even experienced astronomers come away having learned something new for us all to feel more connected to the night sky. So the first section of this talk is called You Are Here. It's basically about understanding the scope and size of the cosmos and our place within it. Then I go over some basics of astronomy, and then we're going to go on a brief tour of the solar system and talk about a little bit of fun facts about all of the planets. So you are here. So this is your planet. This is called Earth. It's about 13,000 kilometers in diameter. It is 150 million kilometers away from the sun. That's a distance we define as one astronomical unit because we're chauvinists and we've decided to define everything based on our own planet. The Earth is the largest terrestrial world in the solar system. This slide kind of pulls double duty as the fun fact slide about Earth because most people I think know at least a little bit about this planet. But no, a unique thing about Earth is that it's the only world in our solar system that has liquid water oceans on the surface. So Saturn's moon Titan has liquid methane oceans on its surface. And there are several outer planet moons, Europa, Ganymede, Enceladus, and actually also probably Titan, that have liquid water subsurface oceans. And we have one really big moon. I think we're going to hold questions to the end, right, Kim? Yeah, okay, well, yeah. So our moon is very large, proportional to our planet. Compared to the size of its planet, it's actually the largest moon in the solar system. I think in raw terms, it's like the 5th largest. That's a unique feature of our planet that probably suggestive of how our moon formed. And as you know, Earth is not too hot, not too cold. All you need is a light jacket. So this is a scale representation of both all the worlds of our solar system and also the 4 terrestrial worlds. I already alluded to it. So our sun is a middle-aged G-class yellow dwarf star. So our star is too small to become a black hole, but it is big enough that it will eventually become a red giant and explode in a stellar nova. There are these 4 terrestrial or rocky planets in the inner solar system: Mercury, Venus, Earth, and Mars. And then between Mars and Jupiter is the asteroid belt. We're going to talk about that. Beyond the asteroid belt are the giant planets, the gas giants Jupiter and Saturn, and the ice giants Uranus and Neptune. And beyond Neptune, it's kind of here be dragons. So this is our galaxy. At least this is what we think it looks like. We can't actually take this picture because in order to take this picture of our own galaxy, we'd have to be outside our galaxy. And there's a good chunk of it that we can't see because we can't see through the galactic core. So you can kind of see that cone there represents like this is where we just can't look past. So this is the Milky Way. It's about 100,000 light years in diameter. It is a barred spiral. Up until recently, it was often thought to be a regular spiral, so like there wouldn't be a bar in the middle; it would just be like a straight pinwheel. But we recently discovered that it's actually a barred spiral. It has a supermassive black hole at its center. It has 4 spiral arms at least that emerge from that bar, and our solar system actually lives in a spur. It's of what's called the Orion Cygnus arm between the Perseus and Carina Sagittarius arms. So you see that we named the arms of the galaxy after the constellations that we made up that they go through. And so we're about halfway between the core and the rim, basically around 25,000 light years or so on like a thing that's 100,000 light years in diameter. So yeah, I've often seen this described as the galactic boondocks, but actually, if you think about it, it's really more like the galactic suburbs, right? Like we're kind of halfway between the middle and the edge. But also, stars don't commute from one part of the galaxy to the other, so this isn't really a suburbs. Anyway, our galaxy is one of the largest in the local group, so Andromeda is something about 50% bigger than our galaxy, but the next biggest one, Triangulum, is about 40% smaller, and these 3 are the only like regular spiral galaxies in our local group. All the other galaxies in our local group are smaller dwarf galaxies that are either satellites of those or are regular galaxies in between them. An obvious thing I wanted to touch on here is, people often ask or often come here to change up and say, how can I take a picture of the Milky Way? How can I see the Milky Way? And where can I see the Milky Way? So you can basically see the Milky Way all year round and from anywhere, so long as it's dark enough. The reason why we tend to associate the Milky Way in astronomical circles with summertime is in the summertime we are looking, so because the Milky Way is like a disk that we're inside, in every direction in that 360-degree plane there is a view of the Milky Way. But in the summer we're looking toward the galactic core in Sagittarius, which is way brighter and denser than the galactic rim. In the winter we see the rim. And obviously, there's a few months in the middle of spring and fall where it's like, yeah, technically you could see it, but it's like basically on the horizon. So this is a photo I took of the Milky Way from Stellophane last year in Springfield, Vermont. So this Sagittarius and the core is like near the horizon there. That light pollution dome is probably Boston. And then as you go up along the disk, or like up along the Milky Way, you see this. There's like a sort of cross-shaped constellation that's Cygnus. So that's a good way to find the Milky Way is to look for Cygnus, because Cygnus is sort of swimming through the Milky Way. And then one more thing about this photo: this like light, this little like dot that's kind of arcing to the left there, that's actually the Chinese space station. And I didn't know it was going to pass over when I left my camera up on the hill taking this time lapse. I happened to be standing next to it because I like went back over just to check to see if my camera was working and everything was fine. And then it went over and people were like, "Whoa, it's the International Space Station." And I was like, "I don't know about that." And I looked it up later. It turned out it was the Chinese one. But yeah, so the other in the winter, if you're looking for the anti-core, or like the opposite direction from the core, that's the constellation Auriga. Okay, so a little bit about the basics of astronomy. So in this slide, we're going to talk a little bit about why we see different stars different times of year, and kind of understanding like how the celestial sphere works. So this is the star trail image. You probably have seen pictures like this before. This is one I took here at Jenny Jump in December 2023 during the Geminid meteor shower. So this is actually a 12-hour star trail. My camera was running there for 12 hours that night. And if you actually watch the time-lapse video I took, you can see when I went to bed because I turned off all the lights in the house. So basically the Earth is spinning on one axis like a top, and we spin through the same 360 degrees every day. And if you look north, you will see Polaris. You can see Polaris in this picture. You can see it's actually this little like semicircle here, so Polaris is actually not directly above the North Pole. It's like slightly off by like about a degree. So you would never notice this with the naked eye, but the camera brings it out. So this is the celestial sphere. From our perspective, it looks like we are rotating under a ball that surrounds us. And as you go south and you take the same picture, you would see Polaris sinking lower and lower toward the horizon, and there would be more stars that are not visible from the north that you would then be seeing, toward your southern horizon. At the equator, the Polaris will always be on the northern horizon, and then the south celestial pole will be visible on the southern horizon. So a practical effect of this is that, like, the stuff in between Polaris and the horizon here is stuff that in the northern hemisphere we call circumpolar. So those objects, those stars, we can see them all year round. On the equator, you don't get to see those things all year round, but you see a little bit farther south and a few other extra things. And then this also touches on why we have seasons. I'm going to get back to that. Yeah. So, okay, if we're going around 360 degrees every day, then how come we see different stars at different times of year? Sorry, that's on the next slide. Okay. Yeah, so the word planet comes from the Greek word for wanderer. So we call them planets because they wander relative to the fixed stars that are always in one place. So they occupy this single plane that we call the ecliptic. So when you see the planets, they'll usually be lined up in a row. There are 5 naked eye planets: Mercury, Venus, Mars, Jupiter, and Saturn. 6 if you count Uranus. So Uranus is kind of just barely on the edge of visibility. It is actually bright enough that it was discovered prior to its discovery by people who thought it was a star. So there's like ancient star charts that have Uranus in them, and people like the star disappeared, and they were like, well, I guess maybe it's just worse viewing conditions. Nah, it turns out actually the planet just moved. But yeah, Uranus was discovered telescopically in real terms, and then 7 if you count Earth, because you can actually see Earth; it's all around you. Mercury and Venus are inferior planets, which is not a value judgment against them. It just reflects the fact that they are closer to the sun than we are. So that means that in order to see Mercury and Venus, we have to be looking down. That is to say, toward the sun. So at night, we are looking up, away from the sun, right? So you're only ever going to see Mercury and Venus near to sunset or sunrise because they have to be closer to the sun. Now, the superior planets, all the other planets, those we see at nighttime. And because the planets in the sun are coplanar, we always see them in the same 13 zodiacal constellations. This only shows 12 of the zodiac constellations, but there's actually a 13th one, but they didn't make an astrology sign out of it, so it's not included. But yeah, so I was going to explain how, why the stars change relative to the time of year. So when we think of a day, right, you're probably thinking of 24 hours. But that's just one way to define a day. If you were to define a day based on a solar day, that is from when the sun is on the horizon to when the sun appears again on the same horizon, that would be 24 hours. But for any other star in the sky, it would be 23 hours and 56 minutes. So that seems weird. It seems like there's some time missing. But the reason for this is actually because the Earth is moving through its orbit. So it's not just 360 degrees that we have to turn for the sun to reappear in the same place in the sky. It's 361 degrees. So it's about, or roughly 1 degree every day, 365 degrees, 360 days, or other way around. And also, by the way, we have leap years because our orbit around the sun actually takes 365.25 solar days. So every 4 years, we have to throw an extra day in there in order to make the math line up. There's no reason for the time of our orbit and the time of our rotation to match up in integers, and that's why they don't. Seasons. We experience seasons because the Earth's axis is tilted relative to the ecliptic. In the northern hemisphere, we experience summer when the North Pole is tilted toward the sun, and we experience winter when the North Pole is tilted away from the sun. This is unrelated to the distance between the Earth and the sun, and in fact, we are actually closer to the sun during northern hemisphere winter than we are during northern hemisphere summer. And an interesting fact that you'll observe, right, because the reason that it's getting warmer out now is that the sun is going higher and higher in the sky. We're spending more hours of the day with the sun out, so the ground is getting hotter over the course of the day. The air is getting hotter. The moon exhibits the opposite behavior because the moon is, roughly speaking, on the ecliptic. It's about 5 degrees up below the ecliptic. In the summertime, the moon sits low in the southern sky for us in the northern hemisphere, and in the winter it goes way up in the sky, just like the sun does, during the summer. That's why we had the idea of a snowball moon, shining down onto a cold winter night. So now I'm going to talk about the phases of the moon and why we only see one side. So an exception to the rule that there isn't a relationship between rotation and revolution in integer form is when we have what's called tidal locking. So the moon is tidally locked to the Earth. That means that it rotates in the same amount of time that it takes for it to revolve, meaning it goes around one spin on its axis in the same amount of time it takes to go 360 degrees around the Earth. However, its orbit is not at a constant speed. It's not a circular orbit. It's elliptical. So it speeds up and slows down. So we actually observe this behavior at the bottom right here, which is called libration. So basically what this means is that we actually see a little bit more than 50% of the moon. And so I'm sure a lot of you probably know this from middle school, but worth mentioning the moon's phases. So when the moon is down toward the sun, we have what's called new moon. A lot of people my age remember that from the Twilight book. Then after a few days, we get a waxing crescent. After a week, we get a first quarter, which is a half moon, which is confusing, but it's called first quarter because it's been a week of a month, right? Like it's 1/4 of the moon's orbit. And then 2 weeks in, we get a full moon. 3 weeks in, we get third quarter, waning crescent, and we start again. Is there anything I didn't mention? Oh yeah, from the moon's perspective, the Earth has the opposite phase. So you can see on this diagram, in the moon's new moon, if you were standing on the moon, you'd be seeing a full Earth, and on a full moon, you'd be seeing a new Earth. Third quarter moon looks like a first quarter Earth. But because of the tidal locking, where on Earth we see the moon travel, all the way across the sky, if you were standing on the moon, the Earth would appear to be basically locked in one spot in the sky. It would wiggle a little bit based on the libration, but if you, went beyond a hill that occluded your view of the Earth, it would never come back unless you went back to the other side of the hill, which is kind of cool. So another thing that people often wonder about is like why Earth looks so different from the other worlds of our solar system. Right? Like you look at the moon, you see all these craters. And on Earth, we're not like driving around craters to get across. Well, now with a sinkhole on I-80, we got that, but like, yeah. But so it turns out the Earth does have craters. For instance, this is a really famous one, Meteor Crater in Arizona. As you can see, that object that created that crater almost took out the visitor center. But the difference is that craters on Earth experience erosive processes that don't happen on the moon, either geological or hydrological or wind erosion, which the moon doesn't have. Mars is sort of a middle ground. So this crater here is a crater on Mars, and you see evidence of water erosion happening, but craters can live a lot longer on Mars because Mars has a lot less water than Earth does, and it never exists in the liquid form for an extended period. Panther Mountain is a mountain in upstate New York, which is probably the result of a crater impact, which seems weird because you think of a crater as being a hole in the ground and a mountain as being the opposite. But basically what happened was an object hit the ground, created a crater, and then that filled in with magma to create a protrusion coming up, which is why the mountain is circular. So now I'm going to talk about eclipses. So solar eclipses are actually really cool because they're basically something that only happens on Earth. They're, as far as we know, there's basically no other planet in our solar system. I know people get in the comments section and say, technically, blah, blah, blah. But like realistically speaking, there's no other planet in our solar system that has a total solar eclipse like we do. So that is to say, our moon appears to be 400, or it appears to be the same size as the sun. In reality, the sun is 400 times bigger, but it's 400 times further away, so they appear to be the same size. Now, you might think, well, so, you saw the new moon diagram, you saw the moon's orbital diagram, why don't we have an eclipse once a month? Well, that's because the moon's orbit is inclined relative to the ecliptic, like I said, by 5 degrees. So that means in order for us to have an eclipse, we have to get lucky. We have to have a situation where the moon happens to be passing through the plane of the ecliptic when it's at its new moon phase. The moon passes through the plane of the ecliptic twice every orbit, so we just have to get lucky that it happens on a particular orbit. And as you can see from like the planes sort of being aligned, usually eclipses occur in pairs. So this is what we call an eclipse season. Usually when we get a lunar eclipse, there's a solar eclipse that's 6 months later. So those solar eclipses are going to occur on a narrow band as the Earth passes in front of the sun, and you'll get totality for probably about 2 to maybe 10 minutes. Where you can see the sun's corona and look at the sun without your eclipse glasses on, which you should always have on when you're looking at the sun during an eclipse, except during totality, and you have to be really careful to get them back on before totality ends. On the other hand, a lunar eclipse happens when the moon passes through the Earth's shadow. These are visible across about 50% of the Earth's surface. They're a lot more democratic, like basically, flip a coin, you might get to see it, and they last about 3 to 4 hours. So if the moon's orbit were coplanar with the ecliptic, we would get a solar and lunar eclipse every month. This is a picture of an eclipse on Mars. Technically, this is actually a transit. So this is Mars's moon Phobos, which you can see is big enough that you can tell it's in front of the sun. If you were standing on Mars when this happened, you would definitely notice it getting a little bit dimmer. And if you had eclipse glasses, you could look up and see that Phobos was in front of the sun, but you're not seeing a corona. It's basically more like what we experience as a partial eclipse. So just to give you that example, so this is a comparison of the two eclipse types. This is a picture of Earth during the 2024 April total solar eclipse. So you can see like that's the shadow of the moon and where it's casting on the Earth. And this is a time lapse of a lunar eclipse. So all right, so this is the most confusing and complicated part of this talk, but I promise you, if you understand this, you will understand so much about astronomy. So tidal forces are confusing. You may be familiar, if you've been doing it, if you ever gone surfing, you ever gone fishing, you know that we get 2 high tides every day. And the reason that happens is the moon creates 2 tidal bulges on the Earth. And that is really confusing, right? Because you're like, wait, why would there be 2? Shouldn't there just be 1? Because it would be like the side, like the moon is pulling the ocean up on the side where the moon is on. No, it's 2, and here's why. So if you think about this from the perspective of the Earth, so imagine I'm the Earth, and these are the moon is over by my right arm here. And so what am I feeling at my core? I'm feeling a pull. Okay, you're the moon, right? So you're pulling me, right? So from my core's perspective, I'm being pulled that way. From this hand's perspective, I'm being pulled that way. And from this hand's perspective, I'm being pulled that way. But the pull is stronger here than it is here, and it's stronger here than it is here. So if you center the forces on the center of the Earth, it actually looks like I'm being stretched in both directions. And that's why we have 2 high tides every day. Now, the sun also creates 2 tidal bulges. So at the full and new moon phases, we get an extra strong high tide and an extra strong low tide. We call that the spring tide. And at the half moon phases, we get a milder, what's called a neap tide. All right, so now we're going to take a tour of the solar system. So you may have heard about Mercury going into retrograde. So actually all the planets have retrograde motion. It happens when a planet appears to move backward along the ecliptic. So normally planetary motion is west to east, so that would be from this way to that way. But sometimes when a planet catches up, this reverses for like Mercury when the Earth catches up, or when the planet catches up to the Earth and passes us. And for a superior planet, it reverses when the Earth catches up to the planet and we pass it. I mentioned tidal locking. We talk about how the Earth and the moon are tidally locked. For a long time, astronomers assumed that Mercury was tidally locked to the sun, but it turns out that actually Mercury is in what's called a 3/2 orbital resonance. So its sidereal day is 2/3 of its year. So a solar day on Mercury lasts 2 years, which is a year on Mercury is about 2 months. So, but yeah, this is just an illustration to show you sort of like why this happens, right? So as Earth catches up to Mars, we use Mars in this example. It looks like Mars has turned around and started heading west, and then it flips back around again. So Venus is hell. Venus is known as Earth's sister planet, and it is about the same size as Earth. It's slightly smaller than Earth, but it is covered with a thick blanket of carbon dioxide. Gee, I wonder if that could be bad for us. And that keeps its atmospheric pressure about 100 times thicker than Earth's. It's possible that Venus was cooler and more hospitable at one point in the past, but it probably experienced a runaway greenhouse effect, probably driven by geological processes, not by a civilization on Venus driving SUVs, but who knows. Transits of Venus were critical in understanding the size of the solar system. So because we know Kepler's laws and we can, relate orbital periods to one another, knowing how long it takes Venus to transit the sun is really helpful in doing the geometry of the the solar system size. But actually, the real source for all these distances I've got listed here, to get them accurate, is using radar. With radar, we can get a much more accurate number. Also, by the way, Venus rotates backwards. That is in the sense to say that, like, if you were to curl your fingers in the direction that the solar system orbits, and that the direction the Earth turns and all the other planets turn, and your thumb would be pointing toward the Earth's north pole. On Venus, it's this way. And also, Venus's rotation is very slow. It takes most of its year for the sun to return to the same place in the sky. Oh yeah, one more thing about Venus. So there's been a lot of debate recently about whether or not there is phosphine in Venus's atmosphere. This is a potential biosignature gas. Um, the jury's kind of out on that one, but I think it is like really enticing, this idea that there could be life on Venus. If there's life on Venus, it would probably be in its like cloud layer, not on the surface where lead melts. But I think it's going to take a lot of science to answer that question. Okay, so now let's talk about life on Mars. That's the cool stuff, right? Everybody loves life on Mars. So for centuries, people have believed in life on Mars, and it's possible. It's still possible. We have not ruled out the idea of life on Mars. As I mentioned, we haven't ruled out the idea of life on Venus, but is obviously nothing like life on Earth. So we see very strong evidence of Mars having, from its topography, of having ancient oceans. Like you can really see on the elevation map that like the northern half of the planet looks like a seabed, based on how much lower it is and how many fewer craters there are. So all right, if Mars used to have oceans, where did they go? Well, so Mars is smaller than Earth, and it cooled faster, and it lost its internal dynamo faster than Earth did. So the magnetic field went away, and the sun was able to boil off all the liquids. So was there life? Well, in the 90s, there was this meteorite called the Allen Hills meteorite that it landed in Antarctica. We determined it was from Mars based on its chemical composition, and there's these little like tendril things in it that look like they could be microfossils. There have been papers debunking the papers and papers debunking the debunking of the papers for now about 30 years. So I think I'm willing to say that the debate is still going and the jury's still out on whether the Allen Hills meteorite is compelling. Although at the time the president did go on television to say that we found life on Mars. Mars has some other really cool and interesting features. It's home to our solar system's tallest and largest volcano, Olympus Mons, and its largest canyon, the Mariner Valley, which is like very obvious on both the topographical map and on this picture of Mars. So this canyon's about as wide as the United States. It would make the Grand Canyon look like a small pothole, and maybe like that one in I-80. And it also, Mars is frequently buffeted by planet-wide dust storms, like the one that left Mark Watney stranded on the planet in the movie The Martian. Okay, so now we're going to talk about the difference between asteroids, meteors, and comets. So asteroids are small rocky bodies that orbit the sun. Most asteroids are contained within the belt between Mars and Jupiter, and for the most part, their orbits are nearly circular. Some asteroids orbit outside the belt, including ones that cross the Earth's orbit. Oh, I wonder if that could be hazardous. They are called asteroids because they look like stars. So asteroid, like star-like. Generally, I already mentioned that. When they were first discovered, the largest asteroids were considered planets for about 50-ish years. From about the first asteroid to be discovered is Ceres, which is this one here. So it was considered to be the fifth planet, and then we discovered a bunch more of them. I'm pretty sure. Oh, sorry. Yeah. By the way, the asteroid belt doesn't look like this. If you were standing on a main belt asteroid, it is unlikely you'd be able to see any of the other ones. And actually, the chances of successfully navigating an asteroid belt are about 100%. When NASA sends probes to the outer solar system, they don't consider the asteroid belt to be a threat. But yeah, so I was just going to mention, so Ceres, Vesta, Pallas, and Hygeia were all considered to be planets until about the 1850s. We're not 100% sure why the asteroid belt formed. It also doesn't represent a large amount of matter. You're probably looking at something, I think like 75% of the asteroid belt in this picture by mass. But there are thousands, hundreds of thousands of asteroids. A few clues that might explain why we have an asteroid belt. So Jupiter is really big, and Mars is kind of small, right? So it's possible that there were interactions between these two planets that have something to do with the formation of the asteroid belt. Perhaps Mars would have been a bigger planet like Earth or Venus, but Jupiter ate a lot of the mass, and basically the stuff that's left over is the asteroid belt. Now, an obvious question to ask is whether other solar systems have asteroid belts, and we don't know. We don't have the technology at this point to observe an exoasteroid belt. We've observed a lot of exoplanets. We know a lot about exoplanets, but as far as we know, it's possible that we might be the only solar system that has an asteroid belt, or maybe most solar systems have 2 or 3 of them. So comets are icy bodies that orbit the sun on much more elliptical paths than asteroids do. So they spend most of their time way out beyond Neptune. Probably 99% of their life is spent outside in the outer solar system. Their orbits can range from decades to centuries or even millennia. So like the longest period ones are like 30 to 50,000 years. This picture I took from here at Jenny Jump of the comet Pons Brooks. So that's a Halley type comet. That's a short period comet. So that's a under 200-year orbit. Pons Brooks has a 75-year orbit, so it's going to be back in 2096 or so. They grow this tail because the heat of the sun heats the ices, both water ice, methane ice, nitrogen ice, inside the body of the comet, and sends bits of the comet trailing off into space behind them. So we knew about comets well before asteroids because their tails are so big and long we can see them, with the naked eye. And it's pretty unique that basically every culture on Earth sees comets as like a deeply alarming thing. That it's like, oh God, the sky has changed. There's this thing there, and it's a portent of doom. All right, so this is going to throw everyone's for a loop. So meteors, meteoroids, and meteorites. Okay, so a meteoroid is a small bit of rock that orbits the sun. It's too small to be an asteroid to meteoroid. Usually meteoroids come off of comet tails. So when the Earth passes through the orbit of a comet, then we get a bunch of meteoroids that impact the atmosphere and become meteors. A meteor is a shooting star. And if one of those asteroids survives its encounter with the atmosphere, one of those meteoroids, survives its time as a meteor and lands on the ground, and we can dig it up, then it becomes a meteorite, which is so like a piece of rock that you can take from the ground and say this came from space. And we get meteor showers every time the Earth passes through the orbit of a comet, and we see a bunch of meteors from that comet's tail. So you might be thinking, so whose job is it to protect us from all this stuff? So that's called planetary defense. It's within professional astronomy, mostly started in the 90s. It actually started because a comet struck Jupiter in 1994, and that was like, oh, kind of a wake-up call that like, oh man, these impacts are still happening. So there was a project called SpaceGuard that was launched by the International Astronomical Union, and thanks to SpaceGuard, we know about 90% of the potentially hazardous asteroids in our solar system. And in 2021, NASA launched the DART, which stands for Dual Asteroid Re-erection Test, and that's what this GIF is showing. Here is the DART test. So we successfully altered the orbit of Dimorphos, which is the asteroid moon of Didymos, which is another asteroid. So yeah, asteroids have asteroid moons. And we are expecting it's possible that some of the debris from that could create an artificial meteor shower on Mars. But more importantly, ESA is sending a mission that's going to take a closer look. So we're going to get some more data on how effective it was. But basically, we are in the position now that we're pretty sure we have the technology to divert an asteroid. There is something called ATLAS, the Asteroid Terrestrial Impact Last Alert System. This is a project of NASA. It operates observatories in Hawaii, California, Chile, South Africa, Japan, and Australia. So the purpose of ATLAS is, unlike SpaceGuard, which was basically about like, can we rule out the prospect of another dinosaur killer impact? ATLAS is more about what can we do about smaller objects that are harder to detect but could be a threat, like not an extinction level threat, but could be a threat to a particular region or city. And that's helpful even if we can't redirect them, because we can then pre-position civil defense resources to deal with the damage and treat the wounded. It's probably unlikely that our current technology could redirect a comet, although I'm not the person to ask about that. But then the biggest problem with comets is that, as we mentioned, their orbits are a lot longer. They're coming from a lot farther away, and they could be coming a lot faster. So they would have more energy that we would need to put into redirecting them. All right, so now we're out in the outer solar system. And we're looking at Jupiter and its great red spot. So, like all the giant planets, we cannot see the surface of Jupiter. All we see is the tops of its cloud layer, and it actually spins really fast. So Jupiter has one of the fastest spin rates of all the planets, at least. A day on Jupiter is just 11 hours. Now you might be thinking, like, wait a minute, but if Jupiter doesn't have a surface, what is spinning that can give us a spin rate that is meaningful? The answer is Jupiter's magnetic field is spinning. So that's how we measure that. And it has these light bands that are called zones and dark bands called belts. They actually travel in opposite directions around the planet, and these zones are regions where ammonia is upwelling in the atmosphere, and the bands are regions where, as it cools, it falls back down. So Jupiter's great red spot is actually a hurricane. And it is a hurricane that's larger than our planet. It's probably, I think it's about 2.5 times larger, but I'm old enough to remember when it was 3 times larger. I have living memory of the shrinking of the great red spot, and having seen it through a telescope when I was a kid, and it being a lot bigger than it is now. So the other cool thing about Jupiter is its moons. Jupiter has 4 very large moons. So they are easily visible with a small telescope. If Jupiter weren't there, they would be visible. That's how bright they are to the naked eye. Ganymede is bigger than the planet Mercury. Callisto is bigger than the moon, and Ganymede is bigger than Callisto. So there's a couple moons that are bigger than our moon. Europa is the cool one. It has the largest liquid water ocean in our solar system. We believe it has at least 200% of the Earth's total ocean water volume under its surface. And Io is the most volcanic object in the solar system. Its surface is constantly resurfaced by volcanic activity. And you might be thinking, well, wait a minute, how can there be liquid water so far away from the sun? It's tides, because the tidal heating that Europa experiences both from Jupiter and from the other 3 Galilean moons is enough to keep the inside really warm. That's also the reason why Io is so volcanic. It's also possible that Ganymede and Io might have liquid water subsurface oceans. Ganymede, depending on who you ask, it might be more like a bunch of layers of slush and water. Io, I'm not really sure about. And Callisto is the oldest object in our solar system. Like, the surface of Callisto, as far as we can tell, has not been resurfaced at any point. So now I'm going to talk about Saturn and its beautiful ring system. So Saturn has a very impressive set of rings, but actually all 4 of the giant planets have rings. It just happens to be that we are lucky enough to exist at the same time that Saturn has these big, beautiful rings. So the other 3 have much less impressive ones that were discovered via spacecraft, can be imaged from Earth, but are not visible in a telescope. So basically, rings form when an object, possibly a moon, gets too close to a planet and is ripped apart by tides. So probably what happened is there was a moon that got too close to Saturn. It was ripped into shreds by Saturn's really powerful tides, and that the remains of it are what we see as the rings. These rings are very impressive. They're actually about 270,000 kilometers in diameter, but their height is only about 30 meters. So if you put Saturn in between the Earth and the Moon, the rings would basically go like most of the way between the Earth and the Moon. But if you're on the top of the rings, and the other side, like first base at Yankee Stadium, like would be about the same distance as the bottom of the rings. Yeah. So in a few 100 million years, they're not going to be there. So enjoy them while you can. Titan, I already talked a lot about, and it's interesting. Or ammonia lakes and seas. Enceladus is another ocean moon. Enceladus is probably the most interesting one from the perspective of interrogating it for life, because Enceladus's oceans are very close to the surface. So it's possible we could actually fly a spacecraft like just over the surface and pick up some samples and decide whether Enceladus has any living things swimming around in that ocean. And Mimas is cool because it looks like a Death Star. All right, so now you might be wondering how to properly say Uranus. It is indeed Uranus. So Uranus and Neptune are our ice giants. So they have hydrogen atmospheres like Jupiter and Saturn, but they have a lot of methane ice, which makes them blue. So Uranus was first discovered by William Herschel in 1781, and he also discovered a bunch of nebulas. Specifically, the type of nebula is called planetary nebulas. So a planetary nebula appears, which has nothing to do with planets. It appears when a star goes nova, and we see this like expanding ring or expanding like cloud of dust coming from that star. So he called them planetary nebulas because they look like Uranus, and it's true, there are a few of them that do look like Uranus. Uranus actually rotates on its side, so one of its poles faces the sun for about half of its year, and the other pole faces it for the other half. We don't know why this is, but most speculation revolves around the idea that there was some sort of impact early in Uranus's history. And in a lot of ways, you can think of Neptune as sort of forming the outer boundary of the solar system. I often compare it to the wall from Game of Thrones, in that, like, when you get to the wall, like, you're at the edge of the kingdom, but you're not at the edge of Westeros. The solar system continues beyond Neptune, but in a meaningful way, Neptune forms a border between the outer solar system and the realm beyond. This is because Neptune basically dictates the orbits that are possible for objects in the Kuiper Belt and beyond. So, like, you may know that Pluto's orbit takes it inside the orbit of Neptune. The only reason this is possible is because Pluto has a resonance with Neptune. That means that whenever it's inside Neptune's orbit, Neptune's on the other side of the sun. So anything that came close to Neptune in that sort of orbit got flung out into the outer solar system, or became one of Neptune's moons, or crashed into it. So a lot of people will ask me whether I think Pluto is a planet. I actually think that Pluto is two planets, because we discovered, so in 1978, we discovered Pluto's largest moon, Charon. But it turns out that actually, unlike other planet-moon systems in our solar system, Pluto and Charon actually orbit a common barycenter that is outside the skin of Pluto. So in any two-body system, there's going to be a center of mass that the two bodies will orbit around. But for the Earth and the Moon, or for the Earth and the Sun, that point is inside the larger body. The center of mass of the Sun-Jupiter system is usually a little bit outside the skin of the Sun. That's how heavy Jupiter is. And the center of mass of our overall solar system kind of goes in and out from inside to outside the Sun. But yeah, this basically means that Pluto is a binary planet. And they also unique, Pluto and Charon are actually tidally locked to one another. So on either of the two, the other one will always be at the same point in the sky. And by the way, because the moon is getting farther and farther away from us due to tides, it may one day turn into a binary planet system where the Earth and Moon orbit a common point between them. Okay, so but a lot of you are thinking, yeah, so wait, but I heard that Pluto wasn't a planet anymore. What's going on with that? So in the 2000s, we discovered several planet-like objects beyond Pluto. And for a while, we were kind of getting away with it by saying, like, yeah, but, you know, a planet's got to be bigger than Pluto, all right? Like, we're just going to just say that's the bar. It's like when you go to the amusement park, and it's like, you got to be this tall to ride the ride. You got to be Pluto-sized to be a planet. But then we found one called Eris. And Eris was at the time appeared to be a little bit bigger than Pluto. It actually turns out it's not bigger than Pluto, but it is heavier than Pluto. And that kind of led to this conflict. At the time, Eris was reported as being our 10th planet, but there was a vote at the International Astronomical Union in 2006 to come up with a new definition of planets. No one seems to like this definition, including astronomers, and especially not planetary scientists, who are people who specialize in learning about the planets. So in my opinion, Pluto is a planet, and also Eris is a planet, and there's about 15 planets in our solar system. But I will caution you to say that, like, well, maybe it doesn't really matter if Pluto is a planet. Trust me, Pluto doesn't know whether or not we think it's a planet. The definition of planet obviously carries a lot of like cultural baggage. As I mentioned earlier, it just comes from this idea of like, oh, that's a thing that moves relative to the stars, right? And I also alluded to the fact that the asteroids were for a period considered to be planets. The ancient Greeks considered the moon and the sun to be planets, but not the Earth, because they didn't think the Earth moved. So let's just talk a little bit about that definition that the astronomers, not the planetary scientists, came up with. So they decided that a planet is something that orbits the sun, is massive enough to be in hydrostatic equilibrium, which is a fancy way of saying it is a ball, and it has cleared the area of its orbit. So Pluto meets two of these three criteria, but the last one it's missing because Pluto has a bunch of dust around it, which is basically what all the planets looked like when they were still forming. So I guess Earth became a planet when it cleared its area, and Pluto is still working on it. I think we should come up with a better definition than this, one that includes Pluto. I would also point out that this technically excludes every exoplanet, like planets that orbit other stars are not included in this definition. But I don't think we should do some special pleading where we say there has to be 9 planets and we have to keep all these beautiful planets like Sedna, Eris, Haumea, Make, Gong Gong, Varuna, Quaoar, Ixion, and Orcus left out. So just to leave us from Pluto, this is a picture from the New Horizons probe of Pluto and its moon, Charon. Oh, sorry, it's the double planet Pluto and Charon. So finally, I've left you with a lot of facts and some cool mysteries, and I want to talk about what else is out there. Well, so we, as I've alluded to, we know very little about the outer planets, and we know less about the realm beyond them. The Kuiper Belt, the Oort cloud, the scattered disk are regions beyond Neptune that have not yet been explored. And there is a possibility that there's another planet out there. And when I say planet, in this case, I don't mean a planet like Pluto. I mean a planet like Mars or like Jupiter, a big planet. And that's an open question in astronomy right now. This is sort of a map of like, based on the orbits of these known objects in the outer solar system, where could there be another large planet, which we may have answers for in the near future. We talked a little bit about the possibility of life on other worlds in our solar system, but we really didn't talk about the possibility of life beyond the solar system. If you're interested in that, you should come back for one of my talks on the search for extraterrestrial intelligence. And yeah, the sky is literally the limit. So yeah, this is the time we've reserved for Q&A, and also for me to tell you to follow me on Instagram. I am at the Intergalactic Wanderer.
All right. Thank you, Dan, for another great presentation. So, we're going to be doing a question and answer session. But quick reminder for anyone who might have snuck in during the presentation for our safety. If you need the restroom, that is the porta potty illuminated by red. To my left, your right, it's behind you. We have a little museum area and gift shop. When we go to leave, we are using our headlights because we do not want to get run over or run people over. On the same token, speaking on lights, if we have flashlights or whatnot when we're wandering around, do try and keep those pointed towards the ground. We don't need to accidentally blind people. We do have volunteers manning various telescopes out there. Do feel free to ask them questions. Chances are they'll either have an answer, look up an answer, or make one up completely, so do your research.
Just like ChatGPT.
Unfortunately, not everyone memorizes the distance from Earth to Saturn off the top of their head? I got asked that once last week. I'm like, I don't know. That's what Google's for. So how question and answer is going to work? For those of you here, if you have a question, you're going to raise your hand and wave it about like you just don't care. Keep your hand up until I reach you and pass you the mic of talking. Because chances are, if you have that question, someone else would also like to know the answer. If you put your hand down, I won't be able to see you because I'm practically night blind because I've been staring at devices monitoring chat online. Online chat, you have it easy. Just type in the question and I'll be able to see it. Right, so we're going to start off with the first online question, which is there stuff between galaxies?
Yes, there is stuff between galaxies. There are various types of stuff between galaxies. There are stars that exist between galaxies. There are stars that, as far as we know, orbit our galaxy from really weird distances out in the great nowhere. But there's also gas and dust. So you may have heard that the Milky Way galaxy and the Andromeda galaxy are hurtling toward each other at a breakneck speed and will, in a very short period of time, maybe just as little as a few billion years, will crash into one another. That's actually already happening. So, like, the outer edges of the dust and gas of the Milky Way is already making contact with the Andromeda galaxy. And there may even be rogue planets between galaxies, although I don't quote me on that.
All right, was there a question out there? I see one in the middle. Right.
What's the thing that makes all the dwarf planets called dwarf planets instead of real ones?
It's the International Astronomical Union.
Yeah, a big group of people we have decided are important for making decisions.
It's a bunch of nerds.
You know the feeling. All right. And I lied. That wasn't actually the first question, online question. The first online question is, were the time lapses in the intro video online, were they from the same location, which is here with the roll-off roof observatories, and did we say it's a state park? So not all of those videos are from here at Jenny Jump. I think there's a couple time lapses from a couple different member club events where they hosted star parties. So a couple maybe from there. And yes, we are in a state park. It's Jenny Jump State Park in Hope, New Jersey. Right. Another question out here. Oh, we got an... All right.
Why do black holes go slow instead of fast? Yeah.
Oh, you mean time dilation? Oh man. Do you have time? Do you have time for a college level general relativity class? So the basically. So black holes, it's not really a feature of black holes, it's a feature of gravitational systems. So when you, because gravity has this effect of bending space-time in relativity, as you, like, things that are heavier, and when you're in a more sort of pitched gravitational field, like you would be around a black hole, then your relative time slows down compared to everywhere else in the universe. So from your perspective, you're still, like, when you look at your watch and you time your heartbeats, it looks normal, but for everyone else looking at you, it looks like you've slowed down. I think it would be easier, like, generally, like, when you learn relativity, you start with special, because special is easier to understand. And a lot of special relativity can be done with simpler math. But so I think you want to focus first on the question of why does time slow down as you get closer and closer to the speed of light. And the way that I would explain that in sort of basic terms is that, like, well, one of what Einstein noticed when he came up with the special theory of relativity is that we have this invariant that the speed of light's a constant in every reference frame. So in order for that to be true, then that means that we must disagree about our clocks or our rulers. So like if I'm going closer to the speed of light, then and you're watching me, then basically I'm reporting that like the space in front of me is compressed, and you're reporting that my watch has slowed down.
It also doesn't help that time is actually a very hard thing to measure. It's kind of partially a social construct, and it is relative to your experience. So, when you're young, 5 minutes is forever. Like, your parents said, give me 5 minutes. 30 minutes later, we're finally getting back to it. When you're older, when you're the adults in the situation, 5 minutes, oh, I didn't even notice that flew by. Because as an adult, we've experienced more time, so the longer lengths of time seem less significant. But when you're younger, you haven't experienced that much time, so time feels much, every second seems to count a lot more. So, like I said, time is one of those weird things that we can go on for forever. And
This is true. This is true even outside of relativity, by the way.
just like vegetables are a social construct too.
So is golf.
Anyhow, our next online question is, let's see. Oh, there it is. If when humans colonize Mars, what criteria would need to happen for them to end up being called Martians?
I mean, I guess being a Martian is a social construct, isn't it? Like, I guess, like, maybe
I knew that was gonna get fed back
if
to
you were
me.
born on Mars, I feel like it's fair to call you a Martian. I guess it depends on whether they want to come back. I think the point at which you don't want to get like the point at which you don't want to come back, then you're a Martian.
Right. Perfect. I'm gonna grab this dude and then I'll get back to you.
Hi. Is the sun orbiting anything? Like, does it depend on the Orion spur? And how does the view of our deep sky change if we move around?
So that's a good question. So the sun is orbiting the galactic core, but it's sort of a common misconception. A lot of people think that the sun is orbiting the supermassive black hole at the core, but actually, and I mean that's not false. It is the case that we make an orbit around that supermassive black hole, but in this that would sort of be like saying like, is Jupiter orbiting the Earth? I mean, it goes all the way around, right? But the thing that's really holding the solar system together is the sun. So the thing that's really holding the galaxy together, the thing that like all the stars in the galaxy are orbiting, is the dark matter. Now, the second part of the question was about how our view of deep sky would change if we moved relative to the Orion spur and we're in another part of the galaxy. It would be vastly different. The stars you see with your naked eye are I would say 100% of them are within 3,000 light years, and probably about 99% of them are within about 1,000 light years. So you're basically like, if we were to move relative, like even a few thousand light years away, the stars would all be different. The nebulas would be kind of similar because those are generally farther away than the stars that we see with the naked eye. But, if we were on the other side of the galaxy, the deep sky objects we see would be completely different. The only things that would be pretty much a constant are the things outside the galaxy. So, like, the Andromeda galaxy is probably visible from most parts of the Milky Way. And, obviously it would be different, like there'd be different stars in front of it, there'd be different stuff around it, and there'd maybe be different galaxies that we could see, like, by looking through the core, if we were on the other side of the core or whatever. But, like, the extragalactic things would basically be the same if we were anywhere else in the galaxy.
Right. I saw another question. I believe you.
Yeah. So you said that Jupiter has no solid surface. So theoretically, if the pressure didn't.
It's still on.
Oh.
Just-
Never mind. Sorry.
could you drive a spaceship? Could you drive a spaceship through Jupiter?
Okay, so yeah, the question is whether you could drive a spaceship through Jupiter. So I should be a little bit more precise. We're not sure whether or not Jupiter has a solid core. It's possible that there is an inner core of Jupiter that is solid metallic hydrogen, and the debate over whether it's, is it a liquid down there, is it some sort of gas all the way down, like that has to do with how Jupiter formed. It doesn't have a solid surface in the same sense that Earth does. You probably couldn't construct a spacecraft that could go deep into the bowels of Jupiter. There was a question that I remember seeing about the idea of could you use a submarine on Jupiter? And the answer to that question is no. And the reason you can't use a submarine on Jupiter is that a submarine on Earth is designed for the buoyant properties and the pressure characteristics of water. And so if you were to drop a submarine into the Jupiter atmosphere, the problem is there is a point at which the pressure is appropriate for a submarine, which it wouldn't crumple, but it wouldn't be buoyant because you're in hydrogen instead of water. So it would fall straight through that and then get crushed. So the answer is probably no. We could definitely build an aircraft that could fly in Jupiter's atmosphere, or maybe like a balloon or something. But there's a limit to how far down we could get, just based on material science.
And just ask your question and then.
Okay.
Oh, you had one more, or
Yeah.
Okay.
So if there's nothing solid on Jupiter, how is the water or the liquid contained in the planet? I guess.
It's contained by gravity. It's definitely it's hydrogen as a gas, and then at some layer eventually you'll find hydrogen as a liquid, and then it's possible that at the very core you have hydrogen as a solid, but the thing that holds it together is gravity.
It kind of like how when the astronauts on the ISS show the floating blobs of water, ooh, hey look, gravity makes a sphere.
Europa and the other ocean moons would look very similar to this, but with water rather than hydrogen. So you would have, layers of solid. You have a layer of ice on the outside, and you have a layer of liquid water, and then at the core of it, you might find another layer of ice.
All right, so we got an online question. Online people, if you have any questions, do get them in. I want to make sure we don't leave any out. Our next online question is, how do we keep reporting planets in other star systems, but we don't know of if there's any extra planets just next to our Oort cloud thingy?
That's a great question. So the answer to that is because the planets that we're looking at in other solar systems are really big. And the planets that we think that they're both really big and they're close to their star. So the methods of detecting planets, or extrasolar planets, work based on either the object occluding the star, because it's so big like Jupiter that when it comes in front of the star, then the star visibly dims, or we're basing it on the star sort of wobbling because of the gravity of the planet. And this potential planet 9 that could be out in the Kuiper belt or in the Oort cloud would be something that is smaller than that, but also notably dimmer because it's so far away from our sun. The same reason why we can't know about all the comets, and we routinely discover comets basically 18 months before they hit their perihelion and then go out and disappear for the rest of human history.
All right, there was another question here.
The question was how sunspots are formed on the sun. So I'm pretty sure that sunspots are areas of the sun's atmosphere that are cooler than the surrounding areas, which is why they appear black, while the rest of the sun appears to be white. From space, on the Earth's surface, the sun looks yellow because of the refraction. I think this is because of the sun's magnetic field. I think it's because of irregularities in the sun's magnetic field, but that's just off the top of my head.
I think also some of them they said so when the sun decides to go bleh and off off gas. I don't.
You're talking about a
I,
coronal mass ejection.
yeah, and then whatever's left hanging out there, still attached, kind of cools down. We do see those as sunspots as well.
That makes sense. I'm gonna go with that. We can ask ChatGPT.
There's plenty of resources about these topics on like NASA is a great place to start. A lot of academic sources like colleges have uh, astronomy, astrophysics, various space departments, um, who also would be slightly better equipped to answer these questions. All right. Our next online question. Could a comet even come down like a meteorite? Aren't they made up of a lot of ice?
Well, yeah, but I mean, meteoroids are also have ice in them. Comets have different compositions of ice and rock. If a comet were like to hit the Earth, which they have before, and the most recent one, you will know from what it did to the dinosaurs. Never forget. That like was probably like the thing that hit the Earth was maybe about the size like like 10 to 20 kilometers in diameter. The ice probably mostly boiled off, but the rock that was left over was enough to destroy all like 90% of living things on the planet.
All right, online people, last call to get any questions in. Any other questions? I see one over here.
Hi, question is what causes phenomena such as northern lights?
So the northern lights, the aurora, happens because of those coronal mass ejections. So the sun yeets out a bunch of charged particles into toward the Earth, and then they arrive in like the upper part of Earth's magnetosphere and are sort of guided down toward the North Pole and the South Pole by those magnetic field lines, and then as they impact the atmosphere, they release energy which creates the different colors. And so depending on how active the sun is, we'll get more or less of that. I happen to have been here when the aurora came through, and that was really awesome.
I believe it's similar in function to how we get neon lights.
Yeah.
We excite the things and then they glow.
And they glow at a particular color based on like their atomic characteristics. So it's like at this layer of the atmosphere, this particular particle, it creates this color.
All right. Any other questions? Okay, we got these two more. And
great questions tonight. You guys are really keeping
if
on my
you have
toes.
more questions, I'm sure Dan will be love to ask them.
Why when lunar eclipse happen, why does the moon look red sometimes?
So the moon looks red because to answer that question, I'm going to point out something you probably experienced when the sun goes down. You notice that the sky can often look kind of red, and the sun will look red as it sets, and that's happening because the light from the sun is passing through a like longer line of the Earth's atmosphere. It's passing through more air. So basically, when you see the red moon during a lunar eclipse, what you're seeing every sunset and sunrise on Earth being projected onto the moon.
All right.
So Jupiter's tornado, did it like always have it, or did it take a long time to get it?
We don't know. We don't actually know how old the spot is. It's probably it could be very old, like it could be millions of years old, because it happens to be a phenomenon in hydrostatics that like when you have these rotating wind patterns, you can have a cyclone that lasts an extended period of time. But the fact that it's shrinking now kind of suggests that it's probably not that old. Like it's probably at least a few hundred years old. Is it a few million years old? I don't know.
All right. Excellent questions. Like I said, Dan would probably love to ask more questions. If I let him, he will go all night. Um, and I'm sure some of you might want to try and see anything through the
yeah.
the
You
couple holes we have. So
You might
I
want to
wanna-
go enjoy the sucker holes.
I want to thank you all for joining us not only here on site, but also online. Like I said, do check out our website. It's where you'll find a list of all our upcoming talks, as well as information on our member clubs, because we are a club made up of other clubs. And if you want to get into astronomy, one of the best ways you can do that is to join your local club. Also, check out our social media, our Facebook, Instagram, Discord servers, all great places to ask any questions you weren't able to now. And also just share your images, show off your brand new telescope rig you got. I love to see those interactions. And do hit those like and subscribe on YouTube and Twitch. All the free actions. Let us know we're doing a good job. And if you want, you can also hit those paid options. We are a nonprofit, so we are kept afloat by donations. With that, everyone have a great night. Clearer skies than we have now, and good seeing.